If we want to understand the chemistry of the atmosphere, we have to understand the sources and the fates of the gases. We have to understand how long those gases are going to be in the atmosphere. And so therefore we need to know where those gases come from, how long they stay there, and what is the ultimate fate of those gases. Now, the book's going to go through, and we'll spend more time in other chapters about a lot of the major constituents. Oxygen is a major constituent of the atmosphere, and it provides a number of important roles beyond fueling respiration by organisms. Other gases that we're going to think a lot about are going to be methane, which is radioactively really important, and we're going to try and understand in later chapters where methane comes from and what its ultimate fate is. In addition, we have different oxides of nitrogen that we'll talk about later. Nitrous oxide, which is N2O, and nitric oxide, NO. And by the time we get to somewhere on the order of chapter 7, we're going to start to think about how these are produced out of ecosystems and how they're eventually consumed. We're also going to spend a lot of time thinking about carbon dioxide from both the source of carbon dioxide and its fate in different components of ecosystems. Now, just as an example of thinking about carbon dioxide and how important it is to think about the fates of these gases, is that carbon dioxide ends up being absorbed by different components of different ecosystems. For example, a lot of CO2 is absorbed by the ocean. But it's important to recognize that carbon dioxide is not destroyed when it's absorbed by the ocean. It's still there. And it continues to exchange with the atmosphere. So a lot of the fates of these gases are relatively short term. So carbon dioxide might be absorbed by the ocean or parts of the biosphere, but then quite often the mean residence time in those components is relatively short, and it's going to be released. The authors give the statement about some of the fates of CO2, and they say if all the fossil fuel emissions ceased instantly today, the excess fossil fuel CO2 in the atmosphere, which is about 35% higher than the natural background, or what we would have had pre-industrially, that the CO2 concentrations would decline by 50% within 30 years, and then another 20% within a few centuries. But the remaining 30% excess CO2 would remain in the atmosphere for thousands of years. And that's not because the mean residence time of that CO2 is that long, but because there's so much exchange between the biotic, abiotic components of different ecosystems and the atmosphere. So a lot of that CO2 right now that's being released is being absorbed, for example, by the ocean. And if we shut off all the fossil fuel emissions, our CO2 concentrations would still be elevated for a long time simply because of the exchanges between, for example, the oceans and the atmosphere. Now, lastly, volatile organic compounds are going to be really important to talk about, and we'll talk a little bit about those later. They're an important part of the reactivity of the atmosphere and something to think about too. Now, in the next section, the authors spend a few paragraphs talking about aerosols, and I think this is a pretty good point in the lectures to spend a little bit more time talking about aerosols, which are an important component of the atmospheric system. Now, aerosols are defined as suspensions of either solids or liquid particles in a gas. So if there's solids in the atmosphere like dust, or they're liquids that are there, these are generally considered aerosols. A big source of aerosols in the atmosphere are volcanoes. And there's a whole bunch of different ways that different aerosols get in there, but thinking about volcanoes and their impact on climate is a good example of thinking about aerosols in general. So this is a picture of Mount Pinatubo erupting, and you can see that there's a large quantity of solids and also liquids that end up being released from these volcanoes into the atmosphere. Once they get into the atmosphere, they tend to be dispersed relatively quickly. So this is an example of sulfur dioxide emissions from a volcano in Iceland, and based on the circulation pattern, how those sulfur dioxide particles were transported throughout the atmosphere relatively quickly based on the prevailing winds. This is something that happens pretty frequently to different degrees in the Earth's history. And basically, if you wait a year or two, there's going to be a news story about a different volcano erupting and transporting large quantities of material into the atmosphere. Now, one of the important things that aerosols do is that they reflect light. So if we take a look at a diagram of the consequences of a volcano erupting, that when that volcano erupts, there's a lot of ash that goes into the atmosphere, but a lot of other compounds too, including CO2. But here we're going to focus on sulfur dioxide. And when that sulfur dioxide enters into the atmosphere, it's going to react with water and form sulfuric acid. And then you get the suspension of sulfuric acid, of this tiny liquid, in the atmosphere. And it does a lot of different things once it's in the atmosphere. So for example, there's albedo. It's going to reflect away light, which will have a cooling effect. And then in addition, it's going to serve as a source of nucleation. And it's going to basically generate clouds. And one of the relatively underappreciated components of the Earth has really been what the effect of volcanoes has been on the temperature of the Earth as well as its reactivity. And this is a figure from a pretty seminal paper in 1996 by Hansen that had taken a look at major eruptions of volcanoes and then the consequences for temperature in different parts of the globe. Now, you can see that the temperature anomaly, so how much warmer or cooler it was than it's expected, there's a lot of variation in there. And this is one of the first papers to show or to begin to think about when volcanoes erupted, what the consequences were for global temperatures. This might be a little bit better demonstration of that. Here are some of the major eruptions that had happened. Here's Krakatoa in the late 1800s, and that was one of the largest eruptions that we had, and taking a look also at the temperature anomaly that occurred. And you can see for a lot of these later volcanoes, such as Pinatubo, that there seems to be a cooling of the Earth based on the eruption of the volcano. And that's due to the release of aerosols into the atmosphere that reflect away light and generate clouds. Sometimes these effects can be incredibly large. And so basically 1816 was considered to be the year without a summer. It was one of the last major famines that Europe had had. And this was preceded in 1815 by an eruption at Mount Tambora. And you can see the temperatures that cause almost major crop failure are on the order of a couple degrees Celsius on average. But that was enough to cause widespread crop failure. And that was all being driven by volcanoes erupting and the release of aerosols into the atmosphere that reflected away a lot of light and cooled, at least in the short term, the atmosphere. Now, aerosols serve as cloud condensation nuclei. So because they're relatively small and they're at the right height in the atmosphere, that you get little droplets of rain that form around those aerosols. And one of the major effects of these aerosols is to generate clouds. And in the next section, what we're going to do is discuss a little bit about the effect of clouds and the role that they play in generating climate for different ecosystems.